My esteemed viewers, in the previous tutorials, we learnt that the network layer provides communication service between two hosts, and it was exemplified in at least in 4 tutorials all about how exactly network layer works. In essence, starting at the source host, passing through a series of routers and ending at the destination host, the network layer services every packet that is called as a datagram to flow over the network of routers. And in this tutorial, we start with the next layer, just immediately beneath the network layer, that is data link layer. We will begin with some useful terminology. We will find it convenient in this particular tutorial or in this particular portion of the network to refer the hosts as well as the routers to be simply as nodes, since as we will see shortly, we will not be particularly concerned whether a node is a router or a host. We will also refer to the communication channels that connect adjacent routers and therefore adjacent nodes along the communication paths as links. In order for a datagram, that is the unit, the functional unit of network layer, in order for the datagram to be transferred from source host to destination host, it must be moved over each of the individual links in the end-to-end path. Over a given link, a transmitting node over a given link, that means over a given link somewhere over here, the transmitting node encapsulates the datagram in a link layer frame and transmits the frame into the link, and a receiving node receives the frame and extracts the datagram. And here is the end system, here is another end system, and there is a system of nodes, and in a link layer the well-being of the link is a matter of concern. Okay, it takes care of node to node connectionality. The link layer takes care of node to node connectionality or node to node movement of the frame. Apart from this, it is something like this. In this picture you can see how exactly this particular node is connected to this particular node. It has to pass through 1, 2, 3, 4 networks in the 4th network, and if at all a datagram or a frame is to be passed from this to this, it has to do 1, 2, 3, 4, 5, 6 hops in the links. This is a wireless link, this is a wired link, from here till here there is a wired link, and this is a router, and from router to router, and this is a node, and all of them may be considered to be nodes for the sake of simplicity. Apart from this, there are well-defined functionalities that is attributed to the data link layer. As I said, the first functionality is node to node communication, and the data link layer has to monitor the link. And framing is a second task, and framing would only simply mean putting the datagram of the network layer into some kind of a capsule, some kind of an encapsulation. Okay, and it has interestingly header where the control information of the data link layer is placed, and it will also have trailer. This trailer mostly contains the error correction codes and error detection codes, and this can be called as a trailer and this can be called as a header if the directionality of the movement of the frame happens to be from left to right. A frame consists of a data field in which the network layer datagram is inserted. Of course, the data or the message content, data content of a data link layer frame happens to be the network layer datagram, as we can see in this particular figure very clearly. Link access is another functionality because the link layer it's a medium access control. Okay, particularly this link layer has to face at several locations what is called as the broadcast link. That means multiple contending nodes wants to push their frames into this particular media, and if at all it has to be, if at all it is a point-to-point connectionality, there won't be any problem virtually. However, in case of broadcast links, there is a problem of associating each and every node and providing each and every contesting node the capability for them to pass their respective frames through a broadcast link, that is a single link with a huge bandwidth capacity, of course. There are the media access control protocols which will take care of this particular matter, and they will see to it that multiple contenders trying to push their frames into a single link, a single channel, that is media, the medium will never collide. Okay, so basically the media access control protocol serves to coordinate the frame transmission and also avoids the possible collisions among the multiple frames. Reliable delivery is yet another issue. When a link layer protocol provides reliable delivery service, it guarantees to move each network layer datagram across the link without any error. Recall, and our viewers may kindly recall, that certain transportation layer protocols such as TCP and UDP also for that matter, also provided reliable delivery services by providing checksum as far as errors are concerned. But other reliability issues are missing in UDP, but every other reliability issue is provided by TCP. Okay, TCP blesses the segments with all the reliability required features. And similar to the transportation layer reliable delivery service, a link layer reliable delivery service is often used for links that are prone to high error rate. And let us remember that this link length happens to be to the tune of kilometers, and it can be said, however, link layer reliable delivery can be considered as unnecessary overhead for low bit error links, including fiber, coaxial cable, and many twisted pair copper links. For this reason, many wired link layer protocols do not provide reliable delivery service. As far as current day internet data link layer is concerned, it never provides any reliability related issues and reliability related promises. The other thing is error detection and error correction is the next one, and such bit errors are introduced by signal attenuation and electromagnetic noise. The bit errors are always introduced by signal attenuation and electromagnetic noise. This is done by having the correction or detection is done by having the transmitting node include error detection bits in the frame, and having the, and we are going to go through it in a detailed fashion as to how the error detection protocols will, or error detection algorithms will generate these bits, and these bits will be used effectively by the receiving node to perform an error check. Error detection in the link layer is usually more sophisticated and is implemented in a hardware. This is to be understood because each and every link is to the tune of kilometers, and definitely there is all the possibility of the frames are subjected to errors. Therefore, a link layer has a sophisticated error correction and error detection mechanism. Error correction is similar to error detection, except that a receiver not only detects when the bit errors have occurred in the frame, but also determines exactly where in the frame the errors have occurred. Often identifying this, the corrections will take place, and if at all the errors are not correctable, then the sender will be intimated to retransmit the frame. Apart from this, for 5 functions, the data link layer also provides half duplex and full duplex mode of communication. With full duplex transmission, the nodes at both the ends of the link may transmit packets at the same time with half duplex transmission, a node cannot both transmit and receive at the same point of time. This is one thing that we should add. And for a given communication link, exactly, the link layer protocol, for the most part of it, is implemented in a unit, physical unit called as an adapter. It's also called as an adapter card. It's also called as network interface card, which will look something like this. It is attached in the motherboard, and every adapter card is given address or given a number, physical number, which has an hexadecimal notation. Therefore, it is 88888. There are 48 bits. Okay. Therefore, the address space of this physical address, the address space of this numbers of this network adapter can be uniquely represented in 2 to the power of 48 minus 1 ways. So the address space of this adapter card is very huge, and this adapter card address is also called as MAC address, media access control access. While this MAC address will provide some kind of a physical representation of a node, the IP address will give some kind of a geographical address of the node. So geographical address is to IP address, and the physical representation of a node is to the adapter card address or adapter card number. And this adapter card number will be issued by governing bodies like IEEE and ITAF, that is Internet Engineering Task Force. At the heart of the network adapter is a link layer controller, usually a single special purpose chip that implements many of the link layer services. On the sending side, the controller takes a datagram that has been created and stored in the host memory by the higher layers of the protocol stack. It encapsulates the datagram in a link layer frame and transmits the frame into the communication link following the link access protocol. It is said that an adapter is a semi-autonomous unit. For example, an adapter can receive a frame, determine its frame is in error or not, and discard the frame without notifying other components. So it can accept or it can discard in the node in which it is housed. When receiving a frame, an adapter will interrupt its parent node only if it wants to pass a network layer datagram up the protocol stack. Similarly, when a node passes a datagram down the protocol stack to an adapter, the node fully delegates this particular function to the adapter of transmitting the datagram across that particular link. Now we will move on to the error detection and correction mechanisms. In the previous section, that is in the network layer, we noted that bit level error detection and corruption of bits in a link layer frame sent from one node to the another node physically connected to neighboring node. The entire mechanism of this error detection can be explained with the help of this figure. This figure illustrates the setting for our understanding. Of course, at the sending node, data D to be protected against bit errors. This data is to be protected against bit errors, which will be possibly caused by bit error prone link, because link is also under the control of data link layer. It is augmented with error detection and correction bits, EDC. It is specifically called as EDC. So this correction and detection is augmented or will happen through error detection and correction bits, or EDC will aid the detection and therefore the correction of errors. Typically, the data to be protected includes not only the datagram passed down from the network layer for transmission across the link, but also link level addressing information, sequence numbers, and other fields in the link frame header. Both data, that is both D as well as EDC, are sent to the receiving node in a link level frame, through this bit error prone link. And due to this bit errors involved, D no longer remains to be D, it becomes D dash, inflicted with errors. And EDC will never remain to be EDC, it may be EDC dash. Note that D dash and EDC dash may differ from the original D and EDC as a result of in-transit bit flips or bit errors. The receiver's challenge is to determine whether or not D dash is the same as the original D, given that it has only received D dash and EDC dash. The exact wording of the receiver's decision in this figure, whether we ask whether an error is detected, not whether an error has occurred, is very important. Error detection and correction techniques allow the receiver to sometimes, but not always, detect the bit errors have occurred. Even with the use of error detection bits, there still may be undetected bit errors. This is very important information that our respected viewers should note. Generally, with more sophisticated error detection and correction techniques that is available in this data link layer, I think none of the errors can miss the attention of these protocols or the algorithms. However, it will incur a larger overhead. More computation is needed while to compute and transmit a larger number of error detection and correction bits. Okay, and we have three methods for error detection. Of course, we limit our discussion only to error detection algorithms, and we will just see how error correction will take place in our future tutorials. There are three methods for error detection, and they are collectively called as error detection schemes. Error can be detected through parity bits, through cyclic redundancy schemes, and through checksum. Of course, the checksum has been exemplified and explained when we discussed the transportation layer, how exactly the UDP's checksum and TCP's checksum will really detect the errors. Okay, that is one complement of sum of all the bits available in a segment happens to be the checksum. Therefore, we will just avoid the discussion of this third method, and this will be shifted for our next tutorial because it is very lengthy. It needs a rigorous explanation, and however we will restrict this particular tutorial in explaining or in understanding how exactly errors can be detected through parity bits. Parity bits, by parity we mean same. The parity bits provide a clue as to whether errors have happened or not. However, this scheme is very much primitive because it is very much simple, because this with this implementation still there can be errors. But anyway, for the sake of completeness, let us understand how exactly parity bits will work in order to detect whether errors have happened or not. Parity bit scheme comes in two classes or two types. One is single dimensional parity bits and two dimensional parity bits. One dimensional parity bit, if number of ones are odd, okay, one string is taken, one bit string is taken or bit stream is taken, and number of ones are counted, and if number of ones are odd, then the parity bit is 1, because it requires a bit 1 in order to become even parity. Even parity is the scheme. So for example, here this data consists of 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. Therefore, in order to have even parity, it needs a 1 bit. That is 1. It needs a 1 bit. Okay, therefore 1 is indicated over here. This is one dimensional parity bit. In example 2, we have number of ones to be 10, which is already even. Therefore parity bit is 0. Therefore sender sends the original data along with the parity bit, which is 0, and here this is the original data and it sends 1, because it needs 1, that is 1 bit in order to be even parity bits. Now example 3. Here the data is 1, 2, 3, 4, the parity bit is 0. At the receiver send, this will go, number of ones is 3, parity bit is 0, therefore error has occurred. Okay, the parity bit is 0 here, but when it goes to the receiving end, one of the ones will become 0 for some reason, for the occurrence of error. Therefore now what the receiver receives is a bit stream something like this with only 3 ones, but there the parity bit is mentioned to be 0, therefore the receiver will be able to understand that error has occurred. Example 4. Here 1, 2, 3, 4. The number of ones is 4, therefore it is already an even parity bit, therefore 0 is to be represented. And what data goes is this data, this stream of bits, and with a 0. At the receiver's end, if the data becomes something like this, 1, 1, 0, 0, 0, 0, 2 ones have gone inverted, therefore number of ones are still even. Therefore, see here, once again I repeat, here it is even parity bit scheme and this is 0, and at the receiver ends multiple bits, that is 2 bits will get inverted, 2 ones will get inverted, say let us assume, and then this is the data, okay, with 2 inversion of the bits, inversion of ones, but still it's a even parity bit, and the data indicates the parity bit is 0, therefore the receiver is misguided. That means one-dimensional parity bit scheme falls on its face if multiple bits go for inversion, multiple even number of bits I should say, okay, then it cannot simply recognize, and all the bit inversions in multiple even numbers will go unnoticed. Therefore, two-dimensional parity scheme is introduced in order to avoid certain difficulties associated with one-dimensional parity scheme. It works something like this. Let us say this is the data stream. Okay, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It should be arranged in the form of a matrix. So it can be arranged in the form of a 4 by 4 matrix, and the parity bit is to be computed like this. Now go along the row, the protocol will go along the row. So there are 2 ones, therefore the parity bit is 0. And go along this row, the parity bit is 0 because there are 2 ones. And here there are 3 ones, therefore parity bit is 1. In order to make it a even parity, there should be 1. Okay, here 1, 1, 1, 3 ones are there, therefore it is odd parity. In order to make it even parity, 1 is required. So therefore this is 1. Now, so go along the row, find the parity bits. Now go along the columns, the protocol will go along the columns and it will find the bits, parity bits, which is shown in red. So 1, 1, 1, it is a odd parity. In order to make it even parity, 1 is required. It is 1 and 1, already even parity, therefore it is 0. 1, 1, 1, odd parity, there is 1, 1, 1, it's even parity, therefore it is 0. Now a corner will be left open. This corner should also be filled with a parity bit. So in order to do that, go along the row, it is 1, 1. Go along the column parity bits, that is 1, 1, therefore it is 0. Come along the row parity bits, it is 1, 1, therefore it is 0. So in all the cases it will happen like this only. The column parity bits and row parity bits will really compatible, and it will give this corner parity bit. Now the sender will send along with the data this is the 1 0 1 0 0 1 1 1. Okay, the entire thing will be sent. So numbering, so the number of parity bits here is increased. It is 4 plus 1 5, 5 plus 4 9. 9 parity bits will be sent along with the data. Therefore the parity bits sent along with the data are 1 0 1 0 column parity bits, 0 0 1 1 the row parity bits, and the corner parity bit. Now another example we are taking, so here it is 32 bits, therefore 32 bits can be arranged into 4 rows and 8 columns. Now go along this row, there are 4 ones, therefore it's already even parity 0. Here there are 4 ones, even parity, therefore 0. Here there are 4 ones, it is 0. Here it is again 4 ones, it is 0. Along the column 1 1 1, it is an odd parity, therefore 1 is required. 1 1 1 1, it is even parity. This is also odd parity, 1 is there. So even parity, even parity, even parity, and even is odd parity 1 and odd parity 1. Therefore you go along this row, you have 1 2 3 4 ones, therefore it's already even parity, therefore it is 0, and here after all it is 0, and therefore it is 0. So now this is how it is generated. So now the sender will send along with the data 1 0 1 0 0 0 1 1 0 0 0 0 and 0, all as parity bits. How errors are detected with this? So again the receiver will go through each and every row. Here it goes through, okay, 1 1, it is already 0, it's okay. Now here 0 is surfacing because of error. There is only one single 1 bit, but here the sender has sent with 0, therefore error must have happened along this direction. Okay, it requires 1 actually, if at all. Therefore some error has gone over here in this row. Of course it is difficult to identify whether it has happened here or here, therefore we will locate this row by means of this horizontal line, and the protocol will go along vertical columns. So here 1 2 3, that is odd parity, therefore 1 was there, it's okay. So 1 1 1, it is also odd parity, it is 0 is there, okay, therefore some mistake has happened. And here 0 0 1 1 is there, it's okay. 1 1 0 is there, it's okay. Now along this a vertical line is drawn, because here mistake has happened. Here the mistake has happened. Of course I will make it 0, maybe in order to explain how exactly make it 0. Okay, we will take only 1. Okay, that was done to explain how multiple bit errors can be identified with a 2-dimensional parity bit scheme. So here I repeat, here there is no error, here the error seems to have happened because 0 is indicated by the sender, but here it should have been 1, therefore some mistake has gone through. So here there is no problem, along this row also no problem, along this column no problem, and along this column no problem. Along this column there are 2 ones, there are 2 ones, but here it is 1 is mentioned. Okay, 1 is mentioned, therefore something must have gone through. Okay, it should have been 0, but some mistake has happened along this column, therefore this is identified along this column. Okay, it should have been 0, but here 1 is noticed because the sender has placed this. Therefore a horizontal line along the row, along the row where error was suspected, and along the column where error is suspected, and the intersection of this row and column is the location where bit error has happened. Okay, we will take one more example. We'll take this first. So along this row 1 2 3 4, 1 2 3 4 5, but here it is showing 0. Okay, right. Along this 1 2 3 4 0, it's okay. Along this 1 2 3 0, something must have happened. 1 1 1 2 3 4 0, it's okay. Along the columns 1 2 3, it's okay. 1 2 3, there is some problem over here. Okay, 1 2 3, 1 is required. Here 1 2 3. Okay, therefore this is a place. Okay, we will draw a horizontal line because we have noticed some error over here. Now we will draw a vertical line. We will go through this. 1, yeah, 1 is required. It's correct. Here 1 1 2, yeah, it's okay. It's okay. 1 1 2, therefore 0, it's okay. Here 1 2 3, it is showing 0. Okay, of course this has been sent by the sender, therefore we cannot suspect this. Something might have happened somewhere inside, therefore we have drawn a vertical line over here. We have already drawn a horizontal line over here, horizontal line over here, and vertical line over here. Intersection of vertical line and horizontal line through rows and vertical line through columns will indicate the location where bit errors have happened. If it is 0, make it 1, and if it is 1, make it 0. Okay, therefore two-dimensional parity bit scheme can identify multiple number of errors. Okay, the number of bit errors that it can identify is equal to either number of rows or number of columns, whichever is minimum, because the location should be unique. It should be identifiable by a single line along the row and single line along the column. Okay, therefore when compared to one-dimensional parity bit scheme, because in one-dimensional parity bit scheme, as said earlier, if multiple even number of bits goes for error, then one-dimensional parity bit scheme is misleading. So as far as two-dimensional parity bit scheme is concerned, it is rather robust when compared to one-dimensional parity bit scheme. Apart from identifying multiple bit errors, it will also indicate the locations at which the bits have gone for errors. So with this we will conclude, and this comes to an end of the initial introduction or introductory tutorial for the data link layer. We discussed the functionalities, the primary functionalities of data link layer, and we discussed a principal physical component, which is the property, really a property of the data link layer, that is namely network interface card. Network interface card is given a hexadecimal number, and it represents the physical identity of a node. And we discussed another predominant function in detail, that is error detection. And in that error detection, we discussed one-dimensional parity scheme and two-dimensional parity scheme. In our next tutorial, we will discuss the cyclic redundancy code, a sophisticated error detection mechanism or error detection algorithm or error detection procedure. Until then, bye. And if you liked this video, kindly subscribe to my channel.